Hello and welcome to the Bresenham Line task. This is the first task of the second week, and in this task we will draw some lines. And if we open the C++ section here, we can see that there are two sets of lines. We will compare the Allegro line algorithm with our own implementation, and we will be using the Bresenham line algorithm. And the Bresenham line algorithm solves the problem of how can we represent a mathematical object, for example, a line, on a screen, which is an array of pixels. So what we want to do is we want to convert a starting point and end point of the line and all the pixels that are covered with that line into an image. And the Bresenham line algorithm is one of the most efficient ways to do that when we are doing it with the on the CPU. I'll give you the brief explanation of the Bresenham line algorithm as well. So on this screen here, we can see that we have 2x4 box here, which represents pixels, and we also have a line from one corner to another, which is our line that we want to rasterize. So let us label the pixels here. So those are just pixel coordinates. And on x-axis and y-axis, so on y-axis we have 2 pixels, and on x-axis we have 4 pixels. And the idea of the algorithm is that we see if the line is inside the pixel, then we draw that pixel. And how do we do it mathematically is we see what's the error, and error as in what's the distance between the line and the center of the pixel. So here you can see that the error is 0 because the line is in the center of the pixel. So now we can color that pixel in. We know that this pixel is part of the line. But now the next pixel, what's the next pixel we draw in? And this algorithm will go from left to right in this case. So we want to go from 1 to 2. And we also want the slope 2 minus 1 divided by 4 minus 1. So this is the start or the end of the line in y-axis and the end of the line in x-axis, subtracted by start of the line in y-axis and start of the line in x-axis. So this will be 1 divided by 3. So the slope of the line is 1 divided by 3, so 1/3. And when we step from 1 to 2, we add the slope to the error. So we add 1/3 to the 0, so this will be 1/3. And now we check, is the 1/3 greater than half? Because half represents the boundary between the first and second row. But we can see that this is not true. So we will not progress to the next row. We will color in the same pixel or same row again. Now for the next step, we will once again add the slope to our error. So now this will be 2/3. And we do the check again. So this 2/3, is it greater than half? It is. So now we actually progress to the next row. So we color in the next row. But now, because we changed the rows, the error has changed as well, because now the center of the pixel is not here, it is in this position. So what we do is we take 1 away from the error, and now this will be -1/3. And once again, next step, we will add the slope to our error, and we get 0. And 0, is it greater than half? It is not, so we will keep it in the same row. And that's how we have rasterized the line. There are some caveats. For example, if we have a steeper line, for example, line going this way, This is a steep line, which would mean that we are throwing, if we use this same algorithm as is, we would have to throw in 2 pixels at the same time in one column, but we don't want to do that. Instead, we'll flip it around and we'll start going row-wise. So now we go from bottom to the top, and then the pixel boundaries on this line. And the other caveat is what happens if the slope is negative. So for example, if we have line going from here to here, then the slope is negative, right? And if we are start adding this negative slope to our error, this will never be greater than half. So what we have to do is we have to compare it to is it less than negative half. So what we have to do is we have to flip the polarity of the comparison, and we also have to change the sign. And if all of these combinations of conditions are implemented, then we can throw lines in whatever direction we want. And that's exactly what we want to do in this task, because we have lines in all possible directions. We have all the different slope variants. We have steep lines, we have non-steep lines, we have negative slope lines, we have straight lines going from top to bottom and from left to right. All of these conditions, all of these cases have to be taken into account. So please download the code from here, and you can see this is the contents of the file, so the lines.cpp. And as mentioned, we are using Allegro again, but this time we'll just use it to draw pixels and lines. So if I run the code, let's see what happens. So we can see we have a complete set of lines because Allegro already has implemented this, but we only have 3 lines here, and we can see later what's the code for rendering these lines. So let's look at the code more closely. You can see that we have init, event loop, draw again. We also have Bresenham line. So all these things, init, event loop, draw, they are exactly the same as in Hello Allegro task. But what's different is the draw function. So you can see that now we are clearing the color to the white, and we also have things for the line algorithm. So we have CX, CY, we have R and num lines, so we have 20 lines. So this is the reference. This is where we use the Allegro to draw our lines. Then we have Bresenham. This is where we have to implement the Bresenham line function. But here we can see that we have shifted all the lines by 300 in x-axis. So all the starts and ends have 300 extra, so that's why the red lines are next to it. I can also see that C is set to red. So that's one way to also change the color. We use the string. And then manually, if we are flipping the displays, as we did in the Hello Bresenham, Hello Allegro task. Finally, we see what we have to do here. So that we have Bresenham line. This is one big function. And you can see that all these conditions now have to be checked. So draw lines from left to right. We always want to draw from left to right. So we can see that if the x1 is greater than x2, then we swap the line, swap the end and start points. Then we see what's the delta of y and delta of x. So that's the start and end pixel difference. That's used for calculating the slope, as we can see here. Then we have the error that accumulates, and this is the delta error. So that's the slope, basically. And now there are 4 different possibilities. There is this non-steep lines and steep lines, And for every steep and non-steep line, there's also a possibility of ascending line and descending line. So in this code, we only have the non-steep ascending lines. So that's why we can see the red lines are not steep and they are rising. So you can see that we are going left to right and they are rising, so they are ascending. And yeah, we'll go through the descending case as well. And in home, you have to implement the steep lines from scratch, which is quite simple if you just copy this part and do some changes. So here, total error in our example, it was 1/3. So this is y divided by x. If the delta error is less, so one caveat here as well is Allegro starts counting from up and then increasing as we reach the bottom. So the y-axis is flipped in the code, as opposed to the example that I gave you on the whiteboard. So if the delta error is less than 0, we have a positive change in x, results in negative change in y. So first we set y, so where we draw a pixel, we start at y1, so that's the start point. And then we do the for loop on the x-axis, and we increment by 1. So this x and y also are the pixel coordinates. And then we draw the pixel, and then we add the error to our error counting. We have the slope to the error. And finally, this is where most of our changes will happen. We check if the error is less than half, negative half. If it is less than negative half, we know that we have to go to the next pixel. So we decrement the y coordinate and then we add error plus 1 to error. So let's see if we can implement the descending case as well. So we start at the same y and we also go from left to right with draw pixels. We add to the error, but now this has to change. So as was on the whiteboard, we flip it. So now the error has to be greater than something, and it has to be greater than half. Now, because it's descending, we want the pixels to become lower and lower. So we don't want to decrement, we want to increment here. And finally, error, we want this to go back to 0, right? So this, we have to decrement this by 1. And now if I run the code, you can see that we also have descending lines. So those two new lines are descending lines. And your task is to do this steep line case here. Just have to take this part here and change some things. So there are a lot of different things to change. For example, instead of for looping on x-axis, we have to for loop in y-axis. Then you have to take into account that you have to change the x here, not y, and all those things. So make sure you keep that in mind. And also one more thing, the most common bug in this task is the line is offset by 1 pixel. And this is quite obvious. If you look closely here in the center, this looks symmetrical. But if one line is off by 1 pixel or some other problem, there's two lines next to each other, for example, then this center is not symmetrical, which means there is a bug in your code. So keep that in mind. All the start and end points have to be exactly at the right places.